And these are the expressions I was talking about. So you have got your plasticity index and you have your liquidity index. These things will be needed. So soil strength and deformation parameters have been correlated to PI. So if you want to know how your soil will deform, okay, or the strength it is going to exhibit in terms of these values, it is usually the plasticity index that we use in showing the strength and deformation behaviors of your soil. While this will give us a quantitative measure of the soil's strength. So now, when I have soil samples and my liquid index or liquidity index is less than 0, then I have what we term as semi-solid state. And at that point in time, your soil will exhibit some high strength and then exhibit some brittle behavior. So the slightest thing, it breaks off, and then sudden fracture is expected. Then we have, when you have your liquidity index lying between 0 and 1, then we say you are in the plastic stage. And so intermediate strength is expected. So you see, at the plastic state, intermediate strength is expected and soil deforms like a plastic material. Then when your liquidity value is greater than 1, you are in the liquid state of your sample. And so at that point, so just look at this. When you express all of this and you have your plasticity, and then so you see you are subtracting the plastic limit value from that of the natural water content of the sample. So when you do these deductions and you express and you are getting a value greater than 1, it means this value here, the water content, is high. The amount of water in the sample is too high. That is how come you can make this subtraction and still divide by PI and have a value above 1. And when that happens, it affects the strength of your soil. And so the soil is likely going to have low strength, and then it begins to flow. Consistency. So it's simply, consistency is more or less dealing with viscosity. So it's kind of trying to find out how your sample will behave. Okay, consistency here, we are using it to describe how the feel of the soil at different moisture level. How does it feel if I add water, certain quantity of water, and I want to rub the soil to see how it feels? So for example, if I have peanuts, I buy granite paste and I rub it on my finger, and I have honey, I want to rub it on my finger. Each of these could be the states of the soil sample when you have added certain amount of water to it. And so I want to know how it feels in my hand, or the feeling of it, whether it is stiff, it is hard, it is firm, it is plastic, soft, or very soft. So these terms, when I want to describe soil in this form, then I am dealing with the consistency. And so that one too, I subtract liquid limit minus the water content over the PI, and that will give me what we term as consistency index. So then you can be asked to do your calculation, and after that, they ask you to describe the soil sample as to whether the soil sample is going to be very soft, is going to be soft, is going to be firm, or the soil sample is stiff or very stiff, just by how you feel them in your fingers. So these are the values you can obtain when you do this computation using this formula. Then soil activity is just like trying to find out the busyness of how busy a soil is going to be or behave in the presence of a certain amount of what? Clay. the tiniest clay sample within the soil sample, how is it going to behave? So remember when we were dealing with coarse material and then fine material, there are differences. And we said that coarse materials happen to exhibit good drainage, but then with a certain percentage, allowable percentage of fine. And so when you have fine particles, the likelihood of you having clay and then silt present in that given soil sample is high. And so we want to measure the behavior, okay? We want to measure how much the tiniest clay particle sample within your soil will tend to affect that given soil sample. That is what we term as activity. So A increases the water absorption capacity of the soil. So as your A will increase, then you are going to have the absorption capacity of the soil also increasing. So let's see. Why? Because if I have clay within a soil sample, we all know that sand is a very good drainage material. So when you use sand and you pour water, it doesn't retain it. It will all flow off. But when I have a certain percentage of clay in it, it will absorb the sample, the water I am pouring inside the sample. So activity is something that will help us determine the behavior of our soil with the addition of a given quantity of clay or tiny particles. So then this table is showing us some of the values we need to know. When you calculate, you are given a question and you are asked to determine the activity. After determining the activity, you may be asked to describe, based on the activity value you have gotten, you may be asked to describe the soil sample. So when you have an activity of 0.7 or less, you will say, oh, my soil sample is going to be inactive. It means that sample is not going to have any effect. That tiny particles within the soil sample is not going to have any effect on the sample. And then we have that of normalcy. Here, the reaction will be just the same as any given soil sample at all you might know. Then it begins to exhibit its behavior properly when you have these values. And so very highly active is when you have this value greater than 6. And we have other clay minerals as well, which have got these values, or minerals generally, which have got these values that one will have to take note of. And then we have various soil types and the likely liquid limits, plastic limits, and plasticity index you are to expect. So for example, just by describing or classifying a given soil sample, you know this is sand. You can't compute liquid limits or do your calculation and have liquid limits beyond these values. These are theoretical values that people have tested a given soil sample, a wide range of soil samples, and then they've got these values. And so they are merely things you can use as a guide when you are on the field and maybe you don't have the time to do these tests in the lab and you can describe your soil properly, then you can use some of these things, these charts, to serve as a guide in executing a given project. So we are being asked to calculate plasticity index, liquid index, and then the soil activity. So here, a fine-grained soil has a liquid limit of 300. Liquid limit of 300 LL is equal to 300%. And then the plastic limit PL is equal to what? 55%. The natural water content, W, small w, is given as 80%. And then the clay content is 60%. So now they are telling us to determine the plasticity index. then liquid index, and then the activity. And then we will be asked further to describe. So if the soil were under a concrete slab, so just like within the campus, we have got some slabs all over within the mining department and that of mathematics and what, yes, geomatic area. You know, we have got a lot of slabs being placed there for us to walk over, creating the path, the walkways for us. So with this concrete slab, assuming you determine the properties of the soil and this thing is found within a concrete slab, how will it behave? That is what they are asking us. So plasticity index is equal to liquid limit minus plastic limit. And so you have your plasticity index of 245%. And so to determine your liquidity index, you're going to have the natural water content minus your plastic limits all over plasticity index, which you have calculated, and that will give you 0.1. Now, the activity of the soil is going to be what? The plasticity index 245 over your clay fraction, which was given as 60%. What does that mean? Clay fraction means that that given soil sample, the component of clay within that given soil sample is 60%. That is what this section means. This last line, the clay content. So with that given sample, then determine the state of the soil in the field. So they said we should determine the state of the soil in the field. So based on table 4.4, the soil width Li is equal to 1 is at low end of the plasticity state. So they said we should use table 4.4. Let's see if we find any table like that. So this is, so watch. So you have 0.01 and this is it. And so 0.01 is at the low end because it's closer to 0. So it's going to exhibit some plastic behavior and have some kind of intermediate strength, and your soil is likely going to deform like a plastic material. So then, determine the predominant mineral. So the mineral that is likely going to be present based on this value you have gotten. We should find that we have gotten our activity value to be 4.1. So we want to determine the mineral that is likely going to be present. So on this table, with the activity value of this table, with the activity value of 4.1, it means our sample is going to fall within here. So it is what? Sodium montmorillonite. That is the sample we are going to be dealing with, and that is what is here. So it is then asking us, determine the consequences of water seeping into the soil. So seepage from the lawn watering will cause the soil to expand. So what this is saying is, when you have put your slab with this type of soil, you have a slab over. These are the effects that it is going to exhibit. Because it is clay, it's going to exhibit, and this type of mineral is going to exhibit an expansive behavior of the soil. And with that expansive type of soil, and you are placing a slab on it, what do you think? So because of the water content in the mineral, it will not increase uniformly because it has got so much clay. It will not uniformly increase, okay, under the foundation. So the expansion will not be uniform. More expansion will occur at the edge of the slab because the water content will be greater there. So at the edge of the slab. Why? Because when you are stepping on it, you tend to push the water to the sides of the slab, and so water content will be high, okay, at that portion, and the expansion will be greater at that end. So the concrete foundation will curl upwards, so it begins to exhibit some behavior of swell, and when it dries, it shrinks. That behavior can greatly affect your material.